Yeah, no, but my girlfriend, so my girlfriend, I did that day. My girlfriend used to go shots up front, basically. You feel that? Yeah, that was like right. Yeah, I'm just trying to think. So like right now, but here, somebody for you from Canada? No accident. Up here, my brother. So I talked to him when I was in high school. Before the days, his boys were busy working. He's for a year. He didn't come. You're in the middle of something more like super. Yeah. But there's a reason we didn't say they didn't yeah, it was more. So the thing that I did, that it was pretty smart. There's a whole lot of place at Virginia. But then between Virginia, went back to 2 semesters, 2 semesters, it became and our geology classes. I showed up and I wish I had more math. I wish I actually had more, but I'd showed up these classes for professionals. Yeah, it was. Yeah, I think, I mean, it helps. We're not, so Rob is actually right. The one thing I did say is Rob writes because he's he's way down. We're more users. Right. I don't know anything about what you're talking about. I was there 5 years. For me, it's what I need. I would have washed out. When all of our food. So that was kind of cool. We didn't like it. But with favor, you knew where you were in class. He would change class. You knew where you were in class. I finished the other one. Yeah, chocolate. So he's 10 cigarettes into our 1 hour class. No, it's really good school enough. A professor now. Lisa in the department and that's why I like see it.
Is that the right presentation?
Yeah. So how do I advance this?
I think that we are.
And I see this is a camera, right?
Yes, this is your camera, and that's the live feed camera.
Okay.
Now let's Stephen over
Yeah. So how
advancing because this is duplicated on that.
Yeah.
Happening. Oh, sorry. He is projecting our break slides right now.
Okay.
So,
so it's not-
we'll switch it over.
So I can advance here. I stand here.
Yes, I am almost positive, but I will confirm.
Yeah, I see.
Yeah, and I actually, it's sort of.
Sorry. How should he be advancing slides?
I think the easiest way will be on here. Does that work if you?
Yeah, that's great.
If you hit.
Yeah.
It's a little hard to explain, but there's something about the fact that it has.
There was something happening.
Yeah.
Okay.
Very good. So I use the mouse, right? Okay.
That was working.
Using this.
I think so.
Does it work? No, does not work on that. Let me see.
It's just really slow.
There's a delay.
Let me see. Okay, so now I have one too.
There you go.
I didn't know you could do that. Control L.
Control L.
I didn't know that.
Can you advance your slides?
Do you want to
No,
try
I
the
don't
remote?
need the remote. And the remote has to be.
Do you want to plug it in? I have a USB right there.
Hopefully that will work.
Oh, that's not
But
USB.
if not, I think you can.
Yes, it
just-
is. Ah, right.
Just went out. It'll hopefully come back.
Yeah, I don't need a remote, right? Just here. So maybe not
Oh, I
necessary.
didn't realize it's big. This here, big. My little bag.
Well,
Well, that's bad. Do I need to go get the guy?
I think it's this cable.
It's good.
This cable needs to be replaced.
I don't need the remote control.
There's a USB right here.
Uh,
If you want to plug into that, then it wouldn't affect that one, I think.
I can just use this to advance, right? No, does not.
So yeah, that's.
I think just so. Let's try plugging in your remote right here.
Okay.
Try and reset this. So end slideshow.
Uh-huh. And
Is this how you typically start? Is this from
presenter view,
where use presenter view?
Yeah.
Okay.
Are you telling me you
From beginning?
Switch. This. Okay, great.
So that's, but it's going right here. It's timing it. I don't know if you have times that.
Okay, so now I can do that. Let's see.
Bring the mouse over to the left and come back up on the screen.
Okay, let's see. Oh, this mouse here.
Yeah, it's
so you go back to the
extended.
left.
Okay. So if I can, is that's a page down or? Yeah, okay, so page up. Then now allow me to go back. Okay, let's come back. Okay. So,
I usually use P and N, P for previous and N for next.
So
yeah, that's it. So
when we get started, I'll have to, in fact, why don't I just, yeah, I'm gonna start sharing it on Zoom now. Share screen, this will continue.
Justin for this. And so how many lectures? 50?
Yeah.
Right. Wow.
Are we actual 50?
Yeah, yeah.
Ooh, it's like a milestone.
Yeah, sounds very engaging.
Should we try the
It's just like super
plug
slow.
in here?
They're not
So we have a minute, so if it goes out again, we'll come back.
Oh, it's because there's
Oh, okay.
multiple aspects. I think it is working because it has to go through.
Two different.
Okay, I think it is working up and down too. Can you go back to? All right. If that's how you prefer, that'd be great.
They know.
Family trying to find some rocks. Don't let it. If you can hold it as a different thing, like I did with the water rights on it, I'll talk to you anytime. You want to hear from you? Here's Michigan's phone number, go right over.
So you can spend the weekend?
Yeah, I'm going to spend weekend in Boulder.
Oh, good.
Yeah.
Nice.
Working in Lincoln Boulder for 4 years.
Okay. Nice city.
Yeah.
But it's good weather. It's been cold this week. Yeah. Oh, really? Yeah. Yeah, I feel like what's that? Oh, gold. Yeah.
Are there any seats up here that people want to sit in? I don't take some of these. Okay.
That was mine. You think?
See, I knew I'd take some of these. I didn't realize how much I realized in life until everyone started wearing masks. Oh, yeah. I haven't been able to get them. They're trying so hard.
Just that you guys are capable of saying we're gonna start.
Yeah. Okay. No, I get it.
I said 2 minutes.
Most of
to
the- most of the
everybody
guys
out there just
Oh,
30 seconds ago. So hopefully people start filtering.
So it's good. Yeah.
I'm supposed to be at your teacher all day.
Yeah.
Jen, would you mind if I take your photo when you take the?
No,
photo?
mine at all. And send the photo
Like
to
3
me.
this morning and I forgot all of it.
No, NGW, they are quite serious about not recording.
Yeah.
We're just streaming.
Talk about it a little bit like next year. We should really tell everybody that we're going to be distributing the names of the elections to the attendees unless they opt out. He was like, "What do we get everyone's names?" But really, we should. Other conferences, I think, we get a list of people there. Yeah. But we'd have to give people a chance to opt out. We talked about that at one meeting.
What
There
just
was
we-
too much to figure out. I think it's too late. I feel like we've got this down now. Like this was smooth this year. Then if we
Yeah.
Okay, we're gonna get started here in just about a minute or so. All right, it's with great pleasure and I'm very excited here to have the 2021 Henry Darcy Distinguished Lecturer here today with us, Dr. Chen Zhu. He's a professor of Earth and Atmospheric Sciences at Indiana University. He's also an adjunct professor in the School of Public and Environmental Affairs at the School of Public Health at Indiana University. He specializes in water's reactions with minerals and rocks. Zhu holds a PhD from the Johns Hopkins University, an MSc from the University of Toronto, a BS from the Chengdu College of Geology, and a postdoctoral fellowship at the Woods Hole Oceanographic Institution. Mouthful. Zhu was a Fulbright Scholar and the 2006 recipient of the John Hemm Award from the National Groundwater Association. Dr. Zhu has been elected a Fellow of the American Association for the Advancement of Science, the Mineralogical Society of America, and the Geological Society of America. His book with Greg Anderson, Environmental Applications of Geochemical Modeling, published by the Cambridge University Press, is used as a textbook at universities around the world. Today, Dr. Zhu is going to speak to us on how our geochemical reactions and aquifers connected to climate change mitigation. With that, I want to welcome Dr. Chen Zhu.
Thank you. It's a great pleasure to be here. I love Colorado. I worked and lived 4 years in Boulder and worked for an environmental consulting firm. And then it's called a Geochance, not part of a Tetra Tech. So it's always, I still kicking myself that how can I move out of Colorado? So the Darcy Lecture Series honors French engineer Henry Darcy. As you know, that he discovered the law of Darcy's law that governed the flow in vast medium. 2 years before Darcy's death, he had a very poor health. He resigned from his position in Paris, went back to his hometown, Dijon, and he did those experiments. We are very familiar with this sand carbon experiments. And he did about 200 of these experiments. This is part of his original data. And then he published his Darcy's law in a very thick book called The Public Fountain in the City of Dijon. And he buried Darcy's law in the Appendix D. But that's the history. But here today, we're not only celebrate Darcy, the brilliant engineer, but also Darcy devoted his, he used his knowledge and skill, he devoted his whole life to provide clean water and sanitation to people. At a very young age, he designed the water distribution system for his hometown Dijon, and is a masterpiece of hydro work. The city gave him a bonus that was worth millions. Today, he declined that. City elected a statue and named the plaza after him. And Darcy went on, and he earned the highest decoration in France, the Legion of Honor. He was a very respected man and very diplomatic. Right? So today we face a lot of water resource issues. You will work on various aspects of water resource issues. And in my class, in my water resource classes, I like to remind students that we have 2 billion people in the world, including 22 million Americans, do not have access to safe drinking water. So that's why this is Darcy series lectures for. We need to inspire a new generation of hydrogeologists and hydrologists to work on those important issues. The lecture series was established by NGWA, National Groundwater Association. They have about 11,000 members. The first lecture was John Cherry. In the last few years, lectures gave up along the 100 talks around the world. And my term started in the pandemic, so they extended the term to July this year. And NGWA received about more than 100 requests from 20 countries so far. I'm only being able to do that in the States, and I gave 50 lectures, and I have 8 more to go. The international hosts, they say they will take the lunch check, and I'll visit them later. But next week I'm going to Canada. I offer 3 topics. So we're going to talk about the first lecture, and also offer a topic called hydrogel chemistry. That's what I specialize in, the chemistry part of hydrogeology. Also, I developed this watershed scale model. Oops. Yeah, that's fine. It's on the future water data in Indiana.eu. That we consider the climate change to the end of the century and see how that will affect the hydrology in that area. And I like to say this is a platform that integrates research, teaching, and service. The NGWA, I would like to thank the sponsors. I'd also like to thank the staff at NGWA. They really tremendous work in the pandemic to organize this lecture series. So when you see the title, you're wondering how those seemingly disparate or separate topics, climate change mitigation, aquifers, and kinetics geochemical reaction can be connected. So in the next few minutes, I will show you the connections. Most of you are probably very familiar with this kind of diagram. So this is a temperature above the pre-industrial age. Here are the years. So this 1900, 2000, 2100. The different lines are different scenarios going forward, right? This is an older diagram. It's from COP21, or also called the Paris Accord. That's the United Nations Climate Summit held in 1915, and COP26 was finished in UK last year. And there's new IPCC Intergovernmental Climate Change Commission report come out about 2 weeks ago. But from those meetings, the climate mitigation goal is to achieve below 1.5 degree going forward, if possible, right? And in order to achieve this goal, you need to reach net zero emission about 2050. But according to the International Energy Agency, to reach net zero emission will be virtually impossible without CCUS. So what is CCUS? So CCUS stands for carbon capture, utilization, and storage. So this cartoon illustrated this concept. So you capture the CO2 at a point source like a power plant, and then you transport the CO2 into pipes, into deep favorable geological location, and inject into deep aquifers. So you keep the CO2 there in the deep aquifer for a long time. In that sense, the CO2 is just sequestered from the atmosphere. Now you will also hear the word CCS. This is a term used before they introduced the term utilization into it. And utilization here means like you can use CO2 for enhanced oil recovery, or you can turn CO2 into cement used for construction materials. Now, this idea is also called geological carbon sequestration. And sometimes those two terms are used more broadly than geological carbon sequestration, which is more restrictive, say, in the deep aquifers. Now, a lot of people don't like this diagram, right? Because it implies continued use of fossil fuels. However, negative emission technologies also need to store CO2. For example, something very, very trendy now is direct air capture from the atmosphere. So this is shows here, this is machines produced by the Swiss company Climate Works, like capture CO2 directly from the atmosphere. However, if you capture, let's say, 1 billion tons of CO2 from the atmosphere every year, that will really help to achieve this goal. You need to still store this CO2 somewhere, right? And probably in geologic formations. Other negative emission technologies, something called BECCS, bioenergy with carbon capture and storage. One of these variations of BECCS is that, say, you don't burn coal or natural gas at a power plant, but burn weeds. By going like 500 million to 2 billion weeds, then you remove CO2. from atmosphere, and then you capture the CO2 at the power plant. So they have actually this kind of power plant, one power plant this kind in UK, but you still need to store CO2. Now I read very carefully the newspapers, right? The New York Times, Wall Street Journal, in the last 2 or 3 weeks after the IPCC report release. This is the most sexy part. They will say, oh, okay, so we want to, this is direct capture of CO2 from atmosphere, or the BECCS, so the bioenergy, this, but they don't mention about the storage part. Like we capture a lot of billion tons of CO2, we still need to store CO2. Now it's start here in the North Sea. So here is off the west coast of Norway. So this in this map, this is Norway, this is Denmark, Germany, and this is UK. So the Norwegian all right. So Norwegian national oil company Equinor discovered a giant natural gas field, which they call the Sleipner project. The natural gas contains 9% of CO2. So they built this platform in North Sea and separate the CO2 from natural gas. If they let the CO2 emit into the air, that will increase the Norwegian national CO2 emission by 3%. So the Norwegian government imposed a carbon tax. So it's cheaper for them to inject the CO2 into this sandstone aquifer called the Otisar Formation. And they have been doing that since 1996 at a rate about 1 million tons per year. So if I can use this cartoon to recapture the story a little bit. So the Norwegian national oil company discovered a giant natural gas field. The natural gas contained 9% of CO2. They separate the CO2 from the natural gas, and they're being injected into this sandstone aquifer through one horizontal well at 1 million tons per year since 1996. So by now, like 20 to 25 million tons of CO2 is stored in this system. And the geology in that place is that it gives very good seismic images. So those are the seismic images. This is a plan view. See how CO2 plume enlarge and migrate over time. That's the vertical point view. So this is the world's first industrial scale geological carbon sequestration project. I was a Fulbright scholar in Norway, so I participated in this project, and the Department of Energy here also gave me a grant to work on this project. So if we have like 2,000 to 3,000 Sleipner-like project in the world, that will make a difference and contribute to the climate change mitigation. Close to home in the Illinois Basin, there's an ADM facility turning coal into ethanol. The byproducts of this is that it generates a lot of CO2. So here's the outline in state of Indiana. I live and work here, Bloomington, Indiana. So geologically, we're in the Illinois Basin, right? And in the Illinois Basin, you want to store in this mountain salmon formation. That's what people have been doing. So worldwide, according to the International Energy Agency, we need to store about 50 billion tons of CO2 from power generation and another 50 billion tons from manufacturing process, like steel making or cement making, which is very CO2 emission heavy. Although there are other options, we storing in the CO2 in deep aquifers is a proven technology, mainly because the US has a 50 years experience of enhanced oil recovery. And we have a lot of storage spaces in sedimentary aquifers, 10 times, 100 times that storage space. So I think I have established the connection between the climate change mitigation and also the aquifers. Now let's look at the kinetics of geochemical reactions. So when you inject CO2 into an aquifer, it causes all kinds of geochemical reactions. And so this cartoon illustrates this. So, so in this cartoon, this is a targeted geological formation, like say sandstone or carbonate aquifer. And above that, you want to have multi-layers of low permeability rock serve as a cap rock to prevent the CO2 escape above. CO2 lighter than water. And we know, but people don't know. The journalists don't know that there's no empty space like underground. So the pores there are filled with brine in the first place. So in this cartoon, this is the injection well. Now the inject CO2 is a supercritical CO2. It will form an immiscible phase near the well ball. And then CO2 is going to dissolve into the brine that will acidify the brine. And I don't know whether you have seen people making Coca-Cola in a movie theater. I have seen people doing that. So you have a barrel of water, you put a sugar powder into it, then you inject food grade CO2, right? And that's your Coke. And now Coke is very acidic, pH 2.6. You drink Coke, I see Coke there today is served. It dissolves your teeth, right? Slowly. But here now you have also the temperature is higher, right? So you have a hot, acidic, corrosive fluid slushing around in aquifers. That will dissolve the minerals already in the aquifer, right? And then will precipitate secondary minerals that can change porosity, permeability. So those are all those kind of geochemical reaction occur. Now, you probably all have work experience like that. You have to have a permitting process, right? Application process. So you needed to know the fate, right, of the CO. You store the CO2, and the fate of a CO2 you can be simplified as 4 trapping mechanisms. One is the structural trapping, like say CO2 here, right? Immiscible phase, stopper by low permeability rock. It's a structural trapping. It's like oil gas structural trapping. CO2 is dissolving the brine, this solubility trapping. CO2 is precipitated out as mineral, like calcite, anchorite, tungstenite, and this is a mineral trapping, and CO2 stay in the small pools. This is either residual trapping or capillary trapping. So this is the 4 trapping mechanisms. So among the 4 trapping mechanisms, the mineral trapping is the safest, right? Immobilize the CO2. The free phase CO2 is the least safe. CO2 is lighter than water. If a CO2 find abandoned well, not a capped well, then it can escape above ground, and that can kill people. CO2 escape to overlying drinking water aquifer can acidify the water there and immobilize contaminants like lead and arsenic. So the more CO2 is mineralized, the better, right? So and CO2 can be mineralized through those kind of chemical reactions. So first the CO2, supercritical CO2 or gas CO2 dissolve into water, become aqueous CO2, and then react with minerals like albite, which is very common in aquifers, and precipitate tungstenite, or react with chloride and precipitate anchorite. So now you see the connection with the kinetics of geochemical reactions as well. So those are seemingly separate topics: climate change mitigation, aquifers, hydrogeology, and the geochemistry, like the kinetics geochemical reaction. They are connected through this geological carbon sequestration project. So now we have established the connections. We have identified societal needs, right? And this audience knows very well. So before you do anything, you do even the conceptualization, permitting application, injection, and post-injection monitoring period. You all need to do hydrological modeling, the fate of a CO2, like in order to get things going. The fate of a CO2 then, in a simplified way, it's the 4 trapping mechanism that how that evolves through space and time. And if we have thousands of projects, there's a lot of hydrological modeling, right? So we have a societal needs there. I will leave the structural modeling and structure trapping and the capillary trapping to others. But as someone to work on the chemical part, like solubility trapping and mineral trapping is my job. And we do this kind of modeling through geochemical modeling, right? Geochemical modeling. And I have a book with my former advisor, Greg Anderson, on geochemical modeling. And in this book, we show very clearly that for any geochemical model, you need 3 pieces, and you need to put them together. One is that you have an input file. That's your conceptual design of the model, and also have the site-specific information. And then you need to have a code, computer code, and then you need to do also have a thermodynamic kinetic database, which contains things like gas solubility, the mineral solubility, the rate constancy, how fast or how slow these chemical reactions are. And this part is a very basic science, right? This part is very basic science. So now you see the connection between basic science and societal needs here. So usually something very basic, very fundamental, things like thermodynamic and kinetic properties of gases, minerals, and surfaces. But in this case, there's a very good connection of the basic fundamental science with very large societal needs. So first we need to know is how much CO2 can be dissolved into water, right? So it's the CO2 solubility. I think we have a very good handle of that. We have a paper published in 2006, and it seems like most people working on CCUS is using our model. So the CO2 solubility is a function of temperature, pressure, and salinity. The increased pressure, you have more CO2 dissolving into it. Increase temperature, you have less CO2 dissolving, and increase salinity, you have a salting out effect, so less CO2 is dissolved into it. I think that's no problem. The problem is, the challenge is that the captured CO2 is not 100% pure CO2. You have impurities like H2S and many others. Now it's cost prohibitive to separate impurities from CO2. It's also not necessary. But we need to figure out what's the solubility of those trace gases like H2S and others. And even they have like the concentration very low, like a few hundred ppm, parts per million, it can change the physical chemical properties very dramatically. So I collaborate with chemical engineers and we work on the H2S solubility. Now those equations are, these papers have a very long equations and very difficult to calculate by yourself. So I had the computer science undergrad students, they programmed into online applications, so people just can type in the temperature, pressure, salinity, and get this solubilities. And according to this, to Rob and Kevin, they have like 3,000 users per year for these programs. The real challenge is how the geochemical kinetics, how fast or how slow those minerals dissolve and precipitate. This is, at the first place, this is a very challenging subject, and we have many knowledge gaps. So let me give you some background to show you what it means with geochemical kinetics. First, let's define the rates of reaction. So rates of reactions are defined as concentration change versus time. You can also define a more fancy equation, say partial differential equation, the concentration of silica in this equation change over time while keep other conditions the same, like temperature, pH, right? So, and the rates, those rates are a function of pH, temperature, and ion concentration, catalysts, and inhibitors. So let me show you how we usually measure these rates, right? So let's say we want to know the dissolution of quartz, which is very common, like if you learn anything about minerals, that quartz is a very common mineral. It's like 20% in Earth continental crust. It has a relatively simple chemistry, like 1 silica, 2 oxygen, quartz dissolving into water and forming silica acid. So we first find a very good piece of quartz crystal and then crush it into powders and then put in the reactors. And then at a predetermined time, we take the reactors down and analyze the silicon concentrations. And over time, then we develop a concentration versus time curve, right? And then we calculate with this equation, the definition, right, so the rates. So I call this method as the conventional experiment method. We know how to do that. We have doing that since the 1930s. The geologists have been doing that since 1930s, right? So, but if you look at this diagram longer enough, you probably see two things. One is like this is a reaction time here, and in days. And so here, what I highlight here is 1,000 days. So it's very difficult to convince graduate students to do this kind of long-term experiments. And also, you see, when the system approach to equilibrium, chemical equilibrium, the concentration very small. So the uncertainty very large. It's very difficult to measure, right? I have to define something very highly technical, say the near equilibrium rates. So the point here is that we have in this area is far from equilibrium rates, right? And we have like 1,000 experiments since 1930s, right? And the USGS has a comparison of this rate constants. This means those far from equilibrium rates. But in the shaded areas, the near equilibrium region, if you look at the surface water, groundwater, and soil water, they're all in this region. But the near equilibrium rates are very difficult to measure because the reaction very slow, and also because the secondary phase is precipitate. So we don't have this kind of data we need where we need. So we need some innovations. So this is the hard science part of this my talk, and I'll go to application 2. The Darcy lecture is supposed to choose the creative, groundbreaking science part of it. Okay, so the one innovation is that we can not using concentrations, but using the isotope ratios, right? And this way will give us 2 orders magnitude more detection sensitivity, and also we are able to measure rates when secondary phase precipitate. Now, so this is an example of the conventional method. So this is the concentration. This is the dates. But if you do experiments and measure the ratios, you can easily resolve dissolution rates, right? Dissolution rate. But here, conventional method can. Part of the reason we can use that is the technology advancement. So this instrument called multiple collector ICP-MS. It's here showing the picture. It probably cost about $1.5 million. It cost another $1 million to renovate the space to host that. But that makes something called non-traditional stable isotope much easier. Right? You can measure the silicon isotopes in 1950s, but you get a better chance to get a cell killed to get that rather than get good data, right? But now you can measure much easier. Well, it's still difficult, but it's possible. Like it's fast, it's efficient. You can measure large numbers. So so in the last 5-10 years, my students, my collaborators, we put this method together, right? And it's the method mature. Now, people in university like to say it is groundbreaking, innovative, things like that. But in a sense, this is not innovation. That's certainly not my invention. In the 1940s, when the chemists who won Nobel Prize by discovering those isotopes, they already thought about it, right? But at that time, it's very difficult to measure, right? They already have the idea. And biologists have used this method for a long time. But now I think the time mature to use that. Right. Anyhow, then now I needed to show you how that works. Okay, so let's say albite. This is why I'm keep saying the mineral albite, because feldspar are the most abundant mineral in the Earth's crust. Like 50% of the minerals in the Earth's crust are feldspars. So this is a chemical composition. So feldspar have 3 isotopes. Now, isotope means is the word isotope from Greek words, iso, same place, top, iso, same, top, the same place. That's in the periodical table. They're in the same place. So albite has silica has 3 stable isotopes: silicon 28, 29, 30s. The 3 different isotopes, they have the same protons but different neutrons. So silicon 28 have 14 neutron and 14 neutron, 14 proton, but this one, 29 and 2030 have 1 or 2 more protons. But that tiny bit of mass, difference in mass, you can use those instruments to measure this now, right? And this is the natural abundance of this. And then in the laboratory, I prepare a solution that is almost pure 29, then mix them together, and then I can measure the rates by monitoring the changes over time. And so that's the way that's the more sensitive way to measure that. And this is the cartoon that one student made for his thesis defense. So here he has dyed ice cubes, and he put the ice cube in a bottle of water. So instead of measuring the volume change from the ice melting in this bottle, you measuring the color. And so the isotope idea is similar of this. And yeah, as you can see, it's much easier to model than the color change, right? Rather than measure the tiny bit of volume change because the ice melt. So now I show you example how we can measure this, right? So we dissolve this mineral albite in the reactor, and here are the reaction dates, and here's the fraction of silicon 29, and this fraction silicon 28, and you can see a small albite is dissolved into the water, and the silicon 29 decrease and 28 increase, and because the natural albite contains mostly 28. And using the mass balance equation for this isotopes, I can calculate. And this is a conventional method. You see, it's if you measure concentrations, it's the reaction too slow and the uncertainty too big. But the isotope tracing method is it's orders of magnitude more sensitive. So this is a quote unquote innovative science part. Okay, so with this method, let me go through this. Okay, so let's say now we want to know how this mineral, where it's abundant, right, in the sandstones, albite, dissolve as a result of a CO2 storage in the aquifers, right? So we did experiments, let's say at 50 degree and near neutral pH, and here's the reaction time, and this is the saturation index, so this is chemical equilibrium, and we see that after 7 days, the system moved from far from equilibrium to near equilibrium. In this region, the silicon concentration change is very small. The uncertainty is very large, but using the isotope ratios, we still can determine the rates. Okay, so now with this rates, we can see that in this kind of systems, we see the dissolution only, the precipitation, the reverse reaction is not a significant, but the secondary precipitation secondary phases like olefin or kaolinite or immobilized, that's important. And these two reactions are coupled together, and that's how the system approach to the reactions approach in this system. In other words, that we see that the feldspar dissolution under these conditions is irreversible, not a reversible action. But I'll get to the application very soon. But is this again? It's nothing terribly new. If you open any geochemistry textbook, they will tell you the feldspar dissolution is irreversible. But here we dig something very deeper. So almost everyone uses this equation to model those kind of reactions, including myself. But you see that if we apply this model equations into the experimental region, we are modeling the reverse reactions. Or you see, let's say you look at the field data, the soil water, groundwater in the granite reservoirs in Georgia, you put in that in the near equilibrium region as well. You apply this equation, then we are modeling the reverse reaction as well. So this is equivalent to say that part of the lost the chance turning back to shiny metal, or the soils on granite outcrop turning back to granite, but this is not right. So what I'm trying to say is that's how we should model it. We model this irreversible reaction only. Do not allow the reverse reaction to occur, but we should allow the kaolinite precipitate coupled with the kaolin precipitate, and that's how we should model the feldspar dissolution in aquifers that store CO2. Okay, so those seem to be very basic studies, like so those are the thermodynamic kinetics on those geochemical reactions. So you see the CO2 solubility, right, into water, into brine, H2S solubility, and the one that I'm talking about, the reversible, irreversible reaction, those are the rate equations, right? So those kind of results of basic research goes into the thermodynamic kinetic database that used together with the computer codes and input file, we can model the fate of the CO2. in a place like Sleipner. So let's look at the Sleipner in Norway again. So now recall that at the Sleipner project, CO2 is injected into this sandstone aquifer, Otisar sand, and the injection point is near the bottom of the aquifer. Now, the aquifer has a very high porosity, very high permeability. CO2 is lighter than water, so over the time, CO2 moved up and pounded below the sixth sequence of shale. And so this is what the Norwegian oil company called the layer 9, and this is the geological model from the seismic data for the layer 9. And recall that the fate of CO2 from a hydrogeology point of view is a multi-phase flow problem. Like we have two immersible phase, CO2 and water. It's also a reactive flow and transport problem. Like CO2 is dissolving into water, a tiny little bit of water is dissolving into CO2. And then on the top of that, we'll have all those chemical reactions, dissolvement and precipitate. So this is the plume migration over time from the seismic data of the top layer, right? So you see that over time, more CO2 is spilled over to the top layer and also migrated. So that's the image, seismic image released by the Norwegian oil company. And then my students did the hydrological modeling, also multi-phase modeling. There's different software, and so they matched the historical plume migration. In general, the model predicted the plume thickness, CO2 saturation, and the solubility trapping are comparable with the seismic data. And then they put more chemical reactions in the model, right? So the CO2 is dissolving to the brine, so the pH of that acidified brine, so the pH dropped from like 7.5 to 4.5, and the acidified water then is dissolving the albite in the aquifer, and the precipitate. This is a mineral containing the carbonate here, and there's a dumsonite, and here precipitated a dumsonite and anchorite. So this CO2 is mineralized, immobilized. And our modeling results show like in 10,000 years, about 20% of CO2 is mineralized. And we did a similar modeling studies for the Mount Simon sandstone in the Illinois basin. About 20% of CO2 is mineralized in about 10,000 years. So you see that so if our concern is those minerals that containing carbonated precipitate, right? But why I talk about albite? But you see here the overall reaction. So in the overall reaction, the slowest step is the rate limiting step. So dumsonite precipitation is 4 orders of magnitude faster than albite dissolution. So I need now albite dissolution. Okay, so this is a CO2 storage in sedimentary aquifers, right? And the Sleipner project, right? They have been injecting that since 1996 at the rate of about 1 million tons per year. If you want to store CO2 in reactive aquifers, then those kind of geochemical reactions are much, much more prominent. So let's say reactive aquifers, let's say basalt aquifers. Now there are 2 pilot studies in the world, one in Washington State and one in Iceland. So they found that the injected CO2 in those basalt aquifers are mineralized 75% to 95% within 2 years. So here now the reaction are very, very important. And here it's different. So in the basalt aquifers, here you don't have a cap lock, right? You keep the CO2 safe underground, not because you have low permeability cap rock, you rely on CO2 being mineralized very fast. Now, here is another very, very trendy topic, and there are so many startup companies like a mushroom very recently. Now, mining, like say nickel mine, right? You will generate million tons of mine tailings. Like those minerals in the mine tailings, like say brucite, olivine, and the pyroxene, they are reactive. They can react with the rainwater, and turning CO2, right? CO2 into carbonate minerals. So the mining companies want to credit. Say, okay, I generate mine tailings, but I have 1 million tons, 10,000 tons of CO2 that I have the carbon credit, right? And then and so in Quebec, I don't know about Colorado, probably not, but I just heard this number in this province Quebec in Canada alone have 10 billion tons of mine tailings, this kind of tailings, right, from mining. And the companies like Microsoft, they have a lofty goal, say want to achieve net zero emission by 2030, which is not too far away, right? But you cannot do that by just reducing carbon emission from your operations, right? You still need to have trucks moving around. So they need to have credit, right? They need to have credit. And so they'll say, oh, we'll give you $1 million to mining companies. Let's do that together. And we get half the credit as well. So this is something on the rage recently. And those things are happening very fast and probably affiliated with this election and the which party is in the White House, right? But here you highlight, right, that from a scholar point of view, that you needed to know the kinetics, and even you need to know the kinetics very precisely, right? The geologists are used to study those processes very slow, thousands of years, 10,000 years, 100,000 years, but now you're talking about those processes occur in a few years. You need to have more accurate, more precise the science that I'm talking about. Another very important, very trendy topic is something called the enhanced silica weathering or enhanced rock weathering. So the idea is that you want to grind the basalts into powders and apply to all the croplands and some of the forestry. And then you can, if it's done properly, you can remove like 2 gigatons or 4 gigatons of CO2 from the atmosphere per year. And so, but that also requires that we know the geochemical kinetics very precisely. How can you come up with this number, right? So that's you underline the need of science for all this kind of proposals. Now this is a report put out by the end of the last year by the management consulting company McKinsey. Right, McKinsey is the kind of top management consulting company, right? So they consult a lot for industry and the government. So here they put out the numbers in $1 billion. So those are all different kind of a climate change mitigation measures. So here is the CCUS, carbon capture utilization. And here's you turn electrification, turn all the automobiles into electric cars, and you modify the agricultural practice and upgrade the power grids and the hydrogen fuel. And again, those numbers are in $1 billion. And you can see from the report, McKinsey report is that CCUS is not that expensive compared to others. There are environmental consequences. So hydrogeology now, since 1960s, that injecting fluids underground causes seismic activities, right? So those are major concerns. And that's why Germany is not very so enthusiastic about it. They have a lot of experience about geothermal development and low-level seismic activities. I talked about leaking CO2 in drinking water aquifers and acidify aquifer, mobilize the contaminants. You can also, the brine that is displaced by injection CO2 also can contaminate the freshwater aquifers. And there's this issue of a water resource, climate change, and energy nexus, right? So the process we're using more water. So here the diagram should show that how many drought months that will be additional if you outfit the power plants into the carbon capture facility as well. And this is as usually the case, the regions in the world that have most water resource problem, well, things are getting worse. This is a map for complete current and planned CCUS project around the world, right? So if we can store hundreds of billions of CO2 in aquifers, and that will make a difference to climate change mitigations. Now, in the pandemic, we can listen to seminars very far away, right, in different countries. And I listened to many seminars in UK, in Britain, and they gave some very interesting talks. And sometimes they are thinking different because their political climate is different. So they ask the big if question. So what if we actually doing this? We actually implement this plan, and how that will affect, say, hydrogeology or earth sciences. So here's some takeaway points. It would create a new industry that at a scale equivalent to today's oil and gas industry. We need a new generation of earth scientists, right? Bessie talking about the lack of students now, right? So by doing this, saving the world part, maybe we can attract more students and more talented students. And certainly that will be a new golden age of hydrogeology, right? Like I mentioned about, say, we need a 2,000 to 3,000 sliping project at each and every stage of the project. You need to do modeling, right? And we also need to know almost other disciplines of the earth sciences. So if you take the optimistic view, last year the US rejoined the Paris Agreement, right? And there was a new UN climate summit completed last year. And there's a lot of enthusiasm from the private sectors now going into this. To conclude my talk, first, this is the basic science part, right? We advanced isotopic method to study those kinetic reactions, and we did not invent it, we advanced it, but that seems to be very promising. And right now, it's very needed, right? For the ideas of sequester CO2 in mine tailings or sequester CO2 in soil, we really need to know this kinetics very well. The climate change mitigation, aquifers, and the kinetics of geochemical reaction, they seem to be very separate topic, but they are well connected through the geological carbon sequestration. Lastly, I will invite you to think big. Even part of this program is implemented, right? We not store hundreds, billions, and so billions of tons of CO2 that will profoundly affect the field of hydrogeology and water resources. And there are a lot of water resource issues as well. Thank you very much.
Great presentation. I'm sure there's got to be some questions.
I think you mentioned something about salinity is an issue when you look at resources.
Yeah.
Roughly, what are the optimal places where you could actually put it? What do you need water quality wise for?
Okay, so you are not allowed to store CO2 in drinking water aquifers, right? It has to be saline by EPA definition, has more than 10,000 parts per million salts.
What's holding us back? When is pilot programs going to be in place, or is it just seems like Yucca Mountain and other projects just run into this bureaucratic doldrums? What do you think?
You're right. I worked on Yucca Mountain many years ago. 2008 just cut off. Actually, it's very funny that in 2008 they tried to recruit me as an administrative judge. So they want to have 60 panels of judge. They really want to ram the Yucca Mountain project through. So they dismiss all the lawsuits. But at the end, I started working on that in 2000 CCUS. So in 2000, the US backed out of the Kyoto Protocol. Bush and Cheney got into the White House. And then they say, okay, we've done not enough. So we give you $400 million to start with carbon capture and storage. So that, and over the years, it's just going up and down. So you see really almost like straight line going up in the past 12 months, something like that. So politics and economics, who is going to pay for that? Norway has a carbon tax. So the older figure I have, I don't have the latest figure, is that the Norwegian government imposed $55 per ton of CO2 emitted. It cost their national oil company $12 per ton to store in that aquifer. But I also gave this talk at Chevron in March. Oil companies are very aware of this. And if you visit the ExxonMobil's website, they have a proposal. They have a bold plan, $100 billion to store all the CO2 captured in the greater Houston area.
So you said there was about 20 to 25 million tons stored, like off the coast of Norway in that project?
Yes.
Like their project? Has there been like any leaking that you've found, or like it's going in and affecting the ocean in some way?
No, they have done very monitoring, mostly geophysical method, diligently. The aquifer has the ultracell sand has a extremely high porosity and high permeability, and on the top of that, a very thick sequence of shell. So they have not found any issues. It's a much more serious issue, a challenge. Let's say what I show you in Illinois basin, like people live there. So, and there's maybe 100,000 abandoned wells, and some like in Germany in 1890 probably have bad paper records, and the coordinates are probably not right. So that's the reason.
Any other questions? Round of applause. Thank you.
Yeah.